All right, this one is 5E, conservation of momentum with inelastic collisions here. So they say a toy car of mass m, right here, and a toy truck of mass 3m, right here, travel in opposite directions at identical speeds. So this one is going at v, this one's also going v, identical speeds, but not identical velocities, because we'll have to call that velocity negative there. So the truck moves to the right and the car moves to the left. The two toys collide and they stick together. That's very important. They travel off as one object afterwards. So one thing they want you to do is to draw a dashed line around the system. Well, we only have two things here, and they are our system here. So those two things are the system, and there will be no outside forces to these guys from anywhere else. So that means if there's no outside forces to the system, then our system's momentum can't change there. So first thing they want us to do is one of these momentum diagrams. So let me grab the sheet here, move this off to the side, and so diagram the situation. So here's the car's initial momentum, and then we've got the truck's initial momentum and the system's final momentum. So let's say with the car, it's m. I'll make m just one bar wide there. And then I will make how fast it's going. It's going to the left, so it's got to be negative. So let's just do 1, 2, 3, 4. No reason other than I know that that's going to make it work out nice in the end there. So again, you can think about it like this. The car's got a mass of 1. I've just arbitrarily given it a velocity of -4. So its momentum here is its mass times its velocity. So its momentum is -4. For the truck, it's got a momentum of, or excuse me, a mass of 3. So it's got to have 3 bars wide. It's got the same velocity there, so it's got to have 1, 2, 3, 4, excuse me, same speed, not the same velocity because they're in opposite directions. So its speed has got to be 4, and its mass is 3. So this set of blocks represents the truck's momentum. Its momentum will be 3 times 4, so its momentum will be 12. So what's the total momentum of the system beforehand? Well, we've got -4 here and 12 here. So our system's total momentum beforehand is 8. And again, these numbers are arbitrary. It's the concept of the masses being different and the speeds being the same and how much total blocks you have. That's what you got to have here. So you don't necessarily have to go back and change these. But this has got a total momentum of 8. 8 total blocks. Negative blocks here, positive blocks. So we have to have 8 total units of momentum over here. One difference is that now we have the two cars stuck together, the m plus the 3m. So now we have 1, 2, 3, 4 is going to be how wide our block is because that's how much mass it has. So how do we get to 8 blocks if we're 4 wide? It's got to be 2. So that is the total velocity. So let's just say this represented literally -4 meters per second, and this one was going +4 meters per second. Then when they stuck together and moved off, they would be going 2 meters per second. So this thing is 4 by 2, which still gives you a total of 8 there. So next part, they want us to do part C, which is, it says, what if there was a spring between the two cars? So let's picture it like this. Let me draw the situation real quick here. So here is the truck, and so here's the little truck that they've got drawn here. Oh, that's terrible. And then there's a spring right there, and that's attached to the car right there. M and 3M. And the spring is going to, whoops, you can't even see it. The spring is going to fly apart like that. So now let's think about the system's initial momentum. Well, they're just sitting there. They have no velocity, so they have no momentum. So 1, 2, 3, 4 blocks wide, I'll still draw it, but it's got no velocity, so it's got no momentum. That means over here we have to have no momentum. How can that be possible if the two fly apart? Well, this one's going to have a negative momentum, and this one's going to have a positive, and they have to be enough to cancel each other out because we have to keep a momentum of 0. So let's look at the car. The car is going to have a positive velocity this time. It's going to fly off to the right. So I'm going to draw it 1 block wide because it's got a mass of m, and I'm just going to draw it 3 blocks tall here, like that. So we are 1 by 3, so the total momentum of the car is positive 3. The truck's got to cancel that out, but it's got a mass of 3. So 1, 2, 3 wide. So I got to get a total of negative 3 blocks to cancel that out. So I'm already 3 wide, so I'll become 1 down there. So this one's got a mass of 3, a velocity of negative 1, but that gives us a total of negative 3 units of momentum. 3 plus negative 3 gives you 0 total, just like we had in the beginning. Whenever you have an explosion like this, your momentum before is 0, they could have been moving, and your momentum afterwards is 0 as well there. Let's do the kinetic energy of this situation right here. So let me get this one out like this. This is before, this is afterwards. Nothing was moving before, so there's no kinetic energy. Nothing was sitting on a hill, so there's no gravitational potential energy. No work was done on the system, so we don't have to worry about that, but we did have spring energy. Now, again, this is arbitrary, but I'm going to draw mine as 2 wide and 1, 2, 3, 4, 5, 6, 7, 8 tall. And part of this is just because I have worked through it already and know what's going to be an easy number to deal with. So 8 tall there. Now, what about afterwards? Well, there's no hill, so no gravitational potential energy. There's no spring, so no spring potential energy. So we just have kinetic energy, but we'll have kinetic energy for the car. I'll write that in blue. And we'll have kinetic energy for the truck. I'll write that in magenta. The two's kinetic energies together have to add up to be the spring's spring's energy, because we got to conserve energy. It converted from spring energy into the kinetic energy of the car and truck. So let's look at it this way. The car's kinetic energy will be 1/2 times its mass of m times its speed. If you look back on the chart we just did, the car has to have a speed of 3. I made it have. So I'll say 3v, and I'll square all of that. So 1/2 m 9v squared for the car. For the truck, it is going to be 1/2 times its mass of 3m, and its speed was just v squared. So 1/2 m 9v squared and 1/2 3mv squared. Look at everything that's the same here. There's a half in each. There's an m in each. There's a v squared in each. So when I'm comparing the two, the car actually has to have 9 compared to 3. It has to have 3 times the kinetic energy of the truck there. So when I go to do this, I know 2 things. The car's got to have 3 times the energy of the truck, and also that their total has to be the same as this. So I'll do it like this for the car. The car, I'll draw 2 bars wide, just like we had over here, and I'll go 1, 2, 3, 4, 5, 6. I'll go 6 bars tall. So over here, remember I had 8 bars. So I need some more bars over here, so these 2 will represent the truck. So this accomplishes 2 things for me. One is that I've got 8 total, 8 by 2 here, so 8 total bars here, and I've got 6 and 2, so 8 over here, and then 6 here, and 2 here. So all together, I've got 8 on this side, 8 on this side. The other thing that it accomplishes is that this 6 is 3 times the value of that. So the car's kinetic energy is 3 times the value of the truck's. It may seem weird that the car has more kinetic energy than the truck. You may assume because they have equal momentums that they have equal kinetic energies, but it doesn't quite work out that way for kinetic energies because of the square. The velocity matters more than the mass for kinetic energies. One last thing we want to check here, and that is part D. And in part D, they say if there were instead 2 identical toy cars and they were traveling towards each other, in this case, or traveling in opposite directions at identical speeds, how would the momentum diagram change, and what direction would they be traveling after the collision? Justify your answer. So let's say they're traveling in opposite directions at identical speeds. So let's say we have a car going this way. I'll draw that as magenta. So I'll call that car A. And then over here, I'll have traveling that way, car B, going that way. So there's B. And here is A. So A is going to the right, B is going to the left, and this time they're identical, so they have the same mass. Sorry, there it is right there. So now let's do car A's initial momentum. So I am just going to do here 1 block wide by 1, 2, 3, 4 blocks, just like we did on the first one, tall. So this gives you 1 by 4 for a total of 4. This car has the same mass, so 1 wide, but it's going in the negative direction. So 1, 2, 3, 4. So 1 by negative 4. And so its total momentum is negative 4. So 4 and negative 4, that means all together we have no momentum. That means afterwards we have to have no momentum. Now one thing they're not completely clear about here is whether or not they stick together. If they stick together, like in the previous problems, which I think they're assuming because all they changed was them to be identical cars, then they can't have any momentum. So 1, 2, 3, 4 for the mass, but no velocity. They would just come to a dead stop there. Now, if they didn't stick together, they could bounce and then come boom and bounce right back out at the same speeds. Just switch. This one goes to the right and this one goes to the left. That would also then cancel out their momentums, and these two bars would just flip like that. And that would also get us to 0 momentum.